So back in grade 11, this was our fundamental trig identity sheet. And we had 3 types of identities: reciprocal identities, quotient identities, Pythagorean identities. And we learned a couple things that we can do with these identities. One of the things that we can do with the reciprocal and quotient identities is I can square both sides of any one of these 5 identities, and I will get what's below. So if I square both sides of any of these, I will get these and these. Okay, so if cosecant x equals 1 over sine x, then cosecant squared equals 1 squared, which is 1, over sine squared. Okay, tan equals sine over cos, and tan squared equals sine squared over cos squared. Okay, so any of these can be squared. These will not be on your identity sheet. Okay, you need to know that you can take these and square them on either side. So as I said, this is the sheet that we're going to get. You will see them like this. I need to know that anything in that area, I can square both sides, and that identity will still hold true. I could even cube both sides if I wanted to, and that identity would still hold true. For the Pythagorean identities, we rearranged this identity in 2 ways. One of the ways was we kept sine where it was, and we took cosine and moved it to the other side. And that created this identity right here. So cosine, when we move it to the other side, becomes negative cos squared. And the other way that we can rearrange this is we can keep cosine where it is, and we can take sine and move it to the opposite side of the equal sign, and it becomes negative sine squared. These 2 we actually use a lot, so it's important for us to know those identities can be moved. The terms can be moved from one side of the equal sign to the other when I have multiple terms being added and subtracted like that. Okay, the other 2 Pythagorean identities, which are actually they will be on your sheet, are these identities. And they basically just come from dividing every term by sine squared. Or dividing every term by cos squared, and then we generate these 2 new Pythagorean identities. Okay? So the squared versions of these, everything that you see here, and these right here, these are not on your sheet. These are things that I need to know are possible to generate from these identities above. Okay? These ones are on your sheet. These rearranged, these ones that we get from this one are on there. Okay? So let's talk about a couple tips and tricks when we prove trig identities. So when we set up our trig identity proofs, one thing that we do is we will set up a left side and we'll set up a right side, and we don't cross over that line. We will prove the left side and the right side independent of one another and try to make the left side the same as the right side. That's the first goal. The second goal, which I would say I use like 90 to 95% of the time, is I try to get everything in terms of a couple common ratios so that I can potentially cancel things or simplify things and make the left side and right side equal. So we try to make everything sine and cosine if possible. Okay? If I'm adding or subtracting fractions, typically I will find a common denominator, put them together. Other things that I should be aware of is that I can use difference of squares with trig identities. So if I have something like 1 minus sine squared x, that will actually factor into 1 minus sine x, 1 plus sine x. And that's similar to how we would factor something like this, right? Where I have x squared minus 16, so 2 perfect squares, and it factors into x plus 4, x minus 4. Right? So same idea. This is a perfect square and this is a perfect square, so we can factor into difference of squares. Same thing if I have 1 minus cos squared. I can factor that into 1 minus cos x, 1 plus cos x. Okay, and then sometimes it's helpful for us to use power rule with exponents. So instead of expressing something like sine to the exponent 6, I could express that as sine squared cubed. So I know something squared and then cubed. I multiply the exponents together, and that gives me back 6. I wouldn't use this step very often, but I think there were some questions that we did in grade 11 where this was a helpful step. But you probably won't see that 5th one used very often. Okay. So I want to do just like a really quick recap here of a couple identities. These will be like easy to medium ones, like what we did in grade 11. We are not going to use identities ever to prove themselves. And what I mean by that is, if I have an identity and that identity is already on my identity sheet, I don't just use that identity to prove itself, I use a different identity to prove itself. So this is already on the identities above, but we're not going to use the identity to prove itself. We're going to use other identities. Okay, so we are going to prove that this identity is true. So I set up a left side, I set up a right side. I will copy down what's on the left side of the equal sign. I'm going to copy down what's on the right side of the equal sign. That's just our setup. Okay, proper format. 90% of the time, we are going to try to change everything in terms of sine and cosine using our identities. So is there an identity for tan squared x that might allow us to express tan squared x in terms of sine and cosine? Oliver. Perfect. So tan squared x is equal to sine squared over cos squared. So I'm going to take tan squared x, and I'm going to replace it with its identity, sine squared x over cos squared x. This is a quotient identity, as Oliver mentioned. Okay, how about secant squared x? Can I get this in terms of a sine or a cosine? Anyone see anything? Oscar? Okay, so secant squared is equal to 1 over cos squared. So I'm going to replace secant with its identity of 1 over cos squared. All right, I have a fraction that's being added with something. I have a single fraction over here. Probably what I'm going to need to do here is get a common denominator and put these two things on the left side together so that I can get a single fraction. So if we think of this as like 1 over 1, I want to multiply the bottom and top by cos squared to get a common denominator. And then I'm going to put them together. So I'll have sine squared plus cos squared all over the common denominator, cos squared. So this is good. I now have the same denominator on the right side that I have on the left side. That's great. Does anyone see how we might be able to get these tops to be the same? How could I get this to be equal? Lucas?
The Pythagorean Identities, sine squared x, cos squared x equals 1.
Okay, so sine squared x plus cos squared x, right here. Whoops. My pen stopped working here. Did. Okay, give me 2 seconds, guys. Sorry. Okay, so sine squared plus cos squared equals 1. So we're going to replace that with 1 over cos squared. And now I have left side and right side equal. So how we end our proofs, does anyone remember from last year? Athena? Okay, so left side equals right side, and then we usually put, there's 3 options here. The mathematician's humble brag is we put a little box just to be like, we squared it away, we're awesome, we proved it. Many math proofs end with QED, and this is short form for a Latin phrase, quanto ero demonstratum, which basically means which was demonstrated in English. Or we can use IIP, which basically means, stands for identity is proven. Okay, so you can choose one of those 3 things. For all of them, you should have left side equals right side. You can choose box, QED, or IIP to end that with. I always do box personally. So that's our little celebration after we prove it. Okay? All right, let's try another one. We're going to split into left side and right side. And I'm just going to recopy the left side of the equal sign and the right side of the equal sign. Okay, first tip, 90% of the time we try to get things in terms of sine and cosine. That's already done. So does anyone have any ideas of what we might do here? Lexi, what do you think? Yep. Yes, so we can FOIL the difference of squares here. It's in factored form right now. If you're not sure what it is in its FOILed form, so it's actually up here already for us, but you guys won't have that, obviously. So you can do first, outside, inside, last if you want to. So we would do 1 times 1, that would give us 1. We would do 1 times positive sign, that would give us positive sign. We would do negative sign times 1. And then negative sign times positive sign gives us negative sine squared x. The positive sign and the negative sign cancel each other, and that's why we end up with 1 minus sine squared for this. Athena? Yep, perfect. So this is a rearranged Pythagorean identity that says that 1 minus sine squared is actually equal to cos squared. So I'm just going to replace this with its identity, which is cos squared. And now we have left side equals right side.
Does it matter if you were changing the cos squared x to change the left side to 1 minus?
It does not. Yeah, the other thing that we could have done is we could have plugged in 1 minus sine squared here and then just not put this. That's an option as well. So you don't have to work exclusively on one side or the other. You can work on both. Okay, a couple things that I want you guys to notice about my process here as well. When I separate into left side and right side, I recopy the left side and I recopy the right side. There's no equal signs that are needed in front of those at that point because I'm just recopying what we're starting with here. But once I start working on a side, I make sure I have equal signs in between each of my steps. And I sort of leave at least a little bit of space in between my steps so that I can sort of see, if someone else is reading it, which all of you guys are obviously reading this right now, or if I go back to read my own proof, I can kind of see where all the steps are and I can follow my own work. Okay? Also in proofs, we don't typically skip over steps because we're showing definitively that an identity is true. So we make sure that we show individual, piece by piece, why this is equal to this, and equal to this, and equal to this. For something like this first step, for instance, when I FOIL, I'm fine if you guys skip over that step and you write 1 minus sine squared. That would be fine. But make sure that you show enough work in your proof that I could follow it and see what your thoughts are as you were trying to prove. Okay? Okay, I'm going to give you guys a couple minutes head start on this one. And I want you to set up your proof and see what you can try with this guy. Okay, how did we do here? Does anyone have a first step for me? What did you do? Okay, so a couple things that I would look for. So firstly, I usually work with the more complex side to sort of try and simplify that. Also, I'm noticing that the right side doesn't have any signs in it. So probably we might have to do something to express this in terms of cosine. So Lucas, what did you do?
So I started by multiplying the numerator and denominator by 1 plus cos x.
Okay, did you finish this proof?
Yeah.
Okay. I will do it. I'm interested in where it's going. So you did 1 plus cos x on left and right?
Yeah.
Okay.
And then I left it in the bracket in the numerator, but then the denominator I expanded.
Okay.
1 minus cos squared x.
Okay, so you expanded the difference of squares. You get 1 minus cos squared x.
And then I just changed that to sine squared x.
Okay, okay. I like it.
And then I just canceled numerator, denominator, and then stuff.
Great. So that is an option.
Was there an easier way to do it?
Did someone do a different proof? Okay, I'm going to erase this one. This might have been a little bit, that was a good method, Lucas. Some people might not have thought to multiply the 1 plus cos into the bottom and top. So Carol, tell me what you did. So using the rearranged Pythagorean identity for sine, we plug in 1 minus cos squared. And then what, Carol? And then what? Like the cosine and cosine? Only if you don't have 1 minus in front of that. So big thing that we need to remember back from grade 11, I cannot come in and cancel individual cosines when I'm adding or subtracting them from other terms. I certainly could do it if I just had cos squared over cos, then of course I will cancel a cosine out of each. But as soon as I'm adding or subtracting other terms in there, I can't cancel individual terms. But Carol was on the right track, so where would we go from here? Oscar?
Well, wouldn't you just be dividing and divide a negative by a negative thing?
Because I'm subtracting individual terms. So remember we said back from rational expressions in grade 11, if I go to cancel something and it's right next to an addition or subtraction, I have to stop. I can't cancel individual pieces. Like if I have 1 plus x over 1 minus x, I can't cancel the individual x's out, right? They're being added with other terms. I can cancel full groups out if groups are being multiplied. So what do I do? Mathushini. Good. The top is the difference of squares. We can factor it. And then on the bottom, I have a 1 minus cos x. On the top, I have a 1 minus cos x. There's no individual terms that I'm going to cancel here. I'm going to cancel a full group as long as multiplication is happening. And then I have left side equals right side. Okay, Lucas's proof that we did right before this is also a completely valid proof as well. There might be different answers, which is fine. Okay, and then we'll say left side equals right side. Okay, I'm going to introduce to you guys, now that we've done kind of a recap of some of our grade 11 identities and we've reviewed how to prove identities, I'm going to introduce to you guys some new grade 12 identities. So the first one is the transformation identities. And we know back from grade 11 and from our studies in Unit 4 that sine and cosine are very closely related to one another. They're really just shifted versions of one another. Right? They have the same amplitude, they have the same domain, the same range. They're just shifted versions of one another. So they're actually, so in grade 11 we talked about how they're 90-degree shifts of one another. We're going to talk about it in terms of radians though. So cosine and sine are pi over 2 translations from one another horizontally. So if I were to take the cosine function, here's my cosine function over on the graph here. It's the red one. What would I need to do to it to make it the same as the sine equation that's on the graph there? How would I shift it? Would I shift it left or right to make it overlap with the sine graph? Lucas? I would have to shift it pi over 2 to the right for these graphs to overlap with one another. So if I translate the cosine function pi over 2 to the right, that results in the graph of the sine function. Okay, and then similarly, if we were to look at the sine function that's on our graph here, what would I have to do to this black graph to make it overlap with the red graph? How would I shift it? Oscar? Yeah, we would shift it pi over 2 to the left. So this creates 2 transformation identities for us just by observing the graphs of the sine and cosine function. And that is that sine x will equal cosine shifted pi over 2 to the right. So I do a pi over 2 to the right shift by doing minus pi over 2. Okay, and then the other way that we said this was that cos x would be equal to the sine graph shifted pi over 2 to the left, which will be plus pi over 2. Okay, so these identities we basically just get from observing the graphs of the sine and cosine functions. And you'll see these on your identity sheet as well under transformation identities. Okay, even and odd identities. We sort of reviewed these, went over the idea of even and odd functions in our last unit. So cosine is an even function, we said. And that's because it's mirrored. Lexi, you don't like this? That's because it's mirrored on either side of the y-axis. So the left side and the right side of this, they're mirrored, right? And we basically said that the definition of this means that if we use, for instance, pi as an example, pi has a value of -1, and negative pi has a value of -1 as well. They have the same value for the positive version of the angle and the negative version of the angle. So if I have cos of a positive angle, it will actually be equal to the value that I get from the cos of the negative angle. Those two things are equal. Okay, and we can see that very clearly from our examples with positive pi and negative pi. They both have the same y value. Okay, you can see it with -2 pi and positive 2 pi as well. They both have a y value of 1. So that's an even function. Tan and sine are both odd functions. And that's because they have point symmetry on 0, 0. So we can see that with the sine function here. And we can also see it with the tan function here as well. And the definition basically is we can use maybe pi and -2 pi to explain this. They have opposite values. The sine of the positive pi over 2 has a +1 as an answer, and the sine of negative pi over 2 has a -1 as the answer. So to make a statement of equivalency here, we say sine of the negative version of the angle is equal to the opposite of the sine of the positive version of the angle. And that's the same definition with tan as well. Tan of the negative version of an angle is equal to the opposite, so we put a negative in front to do the opposite sign, of the tan with the positive angle. So these are our 3 even and odd identities for sine, cos, and tan. I'm just recopying what we have stated above. And these are also on your sheet, so these are not a memorized thing. I'm just explaining to you guys where these identities are coming from. So 3 even and odd identities. This is also true for like the reciprocals. So if sine is an even function, cosecant is also an even function. Or sorry, sine is an odd function, I should say. Cosecant is also an odd function. If cosine is an even function, secant is also an even function. All right, so those are a couple of our new identities. I'm going to introduce to you guys a couple more new identities that we're going to use, and these are called the cofunction identities. Sophia, can you shut the back door for us there? All right, so what do we know about all the angles in a triangle? All 3 angles in a triangle must, Oscar? They must equal 180 degrees. What's 180 in radians? Skill testing question. Pi. Good. Okay. So 180 in radians is pi. So all these angles in this triangle have to add up to pi. What is 90 degrees in radians? What's a right angle? Lex? Pi over 2. Okay. So if I know that this is pi over 2, or 90, and we know all the triangles' angles have to add up to 180, or pi, what do I know these have to add to? You can give it to me in degrees or in radians. What must these add to if this is 90 degrees? pi over 2 or 90 degrees, right? If this is 90, these must be 90 to add up to 180. In radians, if this is pi over 2, which it is, these must add to pi over 2, right? Together, they must be pi over 2. Agreed? Because then I'll have pi over 2 plus pi over 2, which gives me 180, which is pi. So here's the idea. If I call this x, this must be pi over 2 minus x because they have to add together to give me pi over 2. So let me give you an example in degrees. If I made x 20, I would know this has to be 90 minus 20 to give me 70 so that they add to 90. Agreed? Okay. So this is what we're doing, but in radians. Okay? So we're not using degrees. All right. So we don't need all that. So now that we understand where these labels are coming from, here is my question. If I make x my reference angle, and I'm just going to label these as, let's say, A, B, C for now. So let's say this is A, B, and C. What is sine of x equal to? Oliver? You sure? A over C. Okay. Is there, okay, if I made this my reference angle, and I wanted the same ratio, I want A over C, which trig ratio, given the bottom right angle, pi over 2 minus x, will give me A over C? Athena? Cos of pi over 2 minus x also gives me A over C. So by this logic, we can create the transformation identity that sine x is actually equal to cos of pi over 2 minus x. Okay, similarly, let's talk about cos of x. So if I make my reference angle x, what is the cosine of x in terms of A, B, and C? Cos of x. Lexi. Cos of x is adjacent over hypotenuse to x, which is B over C. Now, if I make the other angle my reference angle, and I want the same ratio, B over C, what's the trig ratio of that angle that will give me B over C? That's the question. Carol? Sine, good, of pi over 2 minus x also gives me opposite over hypotenuse, B over C. So by that logic, I can create the second cofunction identity, which is that cos x equals sine of pi over 2 minus x. Okay, so I'm essentially just using SOHCAHTOA and right-angled triangles to prove that they have the same side ratios. That's all we're saying. Okay, again, you will be given these identities. I'm just showing you where some of these identities are coming from so that you understand why they are identities on our sheets. Okay? From this logic, I can also generate a bunch of other types of identities from this triangle, like with the reciprocal ratios and a bunch of stuff like that. So I could also say that cosecant x would be equal to secant of pi over 2 minus x. So just doing like the reciprocals of these, that still holds true. I could say that secant x is also equal to cosecant of pi over 2 minus x. So again, just taking reciprocals of these, that should still hold true as well. There's lots of other ones that I can generate from here as well. Like I could say that cotangent of x, which is adjacent over hypotenuse, would be the same as tangent of this other angle, which would be opposite over adjacent. So they would give me the same ratios, right? So cotangent of x could be equal to the same thing as tan of pi over 2 minus x, and vice versa, right? Cotangent of pi over 2 minus x could be equal to tan of x. These are not on your sheet. They're not super important, but I'm just kind of showing you that we can create lots of other identities from that as well. Okay? These are the main two that we're going to be working with for this unit. Okay? Okay, and there's more that we could add to this list as well, but we'll leave it there. We're not going to do this because we proved with the triangle above, so we're not going to worry about proving those formally. So that brings us to our last example for this section, which is without a calculator, we're going to try to prove what cos of 9 pi over 14 is equal to and what cos of 5 pi over 14 is equal to using the cofunction identities that we have above. So I'm given the information in this question that sine of pi over 7 is equal to approximately 0.43388. And I want to use this information to see if I can prove A and B here. Okay, so we have cosine, and using the cofunction identities above, we discovered that cos of x is actually equal to sine of pi over 2 minus x. Okay, that's this one right here that we came up with from the triangle. In this case, we have something plugged in for x. We have 9 pi over 4 in for x. So can somebody express to me what this would be equal to in terms of sine if we used this identity? Lucas?
Would that be sine bracket pi over 2 minus 9 pi over 14?
Yeah. So we're just subbing that in for x, right? Great. So we sub it in here and also here. So if I want to subtract pi over 2 and 9 pi over 14, I'm going to need a common denominator. And that common denominator will be 14. So I'll multiply the bottom and top here by 7. I'll get 7 pi over 14. What's 7 pi minus 9 pi? Negative 2 pi over 14, which reduces to what? Oliver? Negative pi over 7. All right, I know what sine of pi over 7 is. I don't really know what sine of negative pi over 7 is. But we did on the previous page just discuss an even and odd properties of our trig function. And the even and odd properties, so particularly for sine has odd properties, which say that sine of a negative angle is equal to, what did we say? Negative sine of the angle. So how can I use this in this question? Sine of the negative pi over 7 should be equal to, Billy? Perfect. You got it. Negative sine of the positive angle. So negative sine of pi over 7. And do we know what this is, given the information in our question? What is it? Oliver? Or Oscar, sorry. Yeah. So we're just using this info above. Okay? So we're going to use a similar thing here. I'm actually going to use the same cofunction identity because we start with cosine again. So if I were to express this in terms of sine, I'm then just making my x equal to 5 pi over 4, and I'm subbing that in here for the sine function. So this should be equal to pi over 2 minus 5 pi over 14. Common denominator, so we already did this in the other question. It was 7 pi over 14. Seven pi minus 5 pi. Sophia? 2 pi, good. And 2 pi over 14 simplifies to what? Athena? Pi over 7. Do we know what sine of pi over 7 is? Lexi? Perfect. The question tells us, right? So no calculator needed with that given information from the question. Just use a cofunction identity to help us solve for the cosine. So far, so good? Can I answer any questions on any of these so far? Lucas?
Can you go back to like the top of the page?
Sure.
When you go from cos x equals b over c to sine, can you just explain what on a triangle what that looks like?
Yes, so cos of x is adjacent over hypotenuse for x as the reference angle. What is adjacent over hypotenuse for x?
So that's the yellow one?
Yep.
Okay. That would be b over c.
Okay, so that's adjacent over hypotenuse. Now if I switch my reference angle to, whoops, was supposed to be a highlighter. If I switch this to my reference angle, what trig ratio will give me the same b over c value?
Sine.
Right, because this becomes opposite and this becomes hypotenuse, right, if this is my reference angle. So we're saying that sine is also equal to b over c.
Okay.
And then by the fact that the ratios are the same, we know that those are equal.
Thank you.
No problem. Okay, guys, so the first part of this,